to remove an electron from a gaseous atom to form a positively charged gaseous ion, we can look at the values and tell the nature, okay? And tell the nature of that element. If the element is a metal, if an element is a non-metal, we can tell if it has 2 electrons in the outermost shell, if it has 1 electron in the outermost shell, depending on the successive ionization energies. Not so? And for instance, you can look at our elements. We have element A. And the element A, the first ionization energy is 495. Okay? And its melting point it's high. I'm sure it's higher than this. Okay? Now, element B, its first ionization energy is 508. First ionization energy is 508. And its melting point is 230. You see, it is high. This one is 790. And look at its melting point. So these 3 elements, their melting points are high. Okay? They have a high melting point. But for this one, you see, its first ionization energy so high, but the melting point, it is even a gas at room temperature. What does that mean? Since the energy required to remove the very last electron, the outermost electron, is high, it means the outermost electron is strongly bound onto the nucleus of that atom. Okay? But for these two, you see, the energy is very low. You need relatively lower energy. It is less than 800. So you need relatively lower energy to remove the outermost electron. You see this? You see this? And their melting points are high. So basing on the melting point and the first ionization energy, we can conclude that element A, element B, and element C, they are metals. Okay? Why? Because the first ionization energy is very low, usually lower than 800, and it's lower than 800. But for element D, with a high with a high first ionization energy and with a very low melting point, you can see, okay, it is minus 20 melting point. So this is either it's a liquid. Now we need to know what is the boiling point to conclude if it's a gas or not. So we shall conclude that D is a non-metal. Okay? Any question for me?
No.
So which one of the elements A, B, C, and D is a metal? Explain your answer. Can you explain your answer?
Yes.
So which of them are metals?
Element A is a metal
And then
because it has the lower first ionization energy
and
and a very high melting point.
a high melting point. That's good. And then B, C, and D, and then B, C, they are also metals. So here your answer was A, comma, B, comma, and C. They are metals. Why? They have a high, okay, first ionization energy, okay, and a high melting point. Okay, so because of these two, then
mm,
they confirm that these elements are metals. But for D is a non-metal. Why? Because did I say high fast ionization energy? They have low fast ionization energy, meaning the outermost electron is loosely bound. But for D has a very high, okay, fast ionization energy, okay, and a very low melting point, which implies that D is a non-metal. And the question is, state the type of bonding between bonding and structure of the oxides of element A and D.
I think it is ionic.
For what?
For A and D,
No, we want the oxides of A and D.
it can be metal oxide.
For what? Okay, it's simple. The question is, you say for A, it forms maybe the bonding, it is this, and the structure that is formed is this. For D, bonding is this, and the structure that is formed is this. Uh-huh. We haven't talked about bonding. Oh, yeah, yeah. Okay, 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 okay. You know, I thought bonding forms sixes, eh? So I thought, I thought you were the ones I thought, eh? Yeah, sorry. So the type of bonding, this is ionic bonding. This is A, and it is a metal, and you are reacting A with oxygen, and oxygen is a non-metal. So the type of bonding between metals and non-metals is ionic. Okay?
Yeah,
And the structure that is formed is a giant ionic structure. Okay? Then for D, the bond is covalent. Okay? That is covalent bonding, and the structure that is formed is a simple molecular structure. Okay? Simple molecular structure. Is that okay?
yeah,
So now I hope you can now tell, you can be able to use the ionization energies. Okay? You can use
mm,
the ionization energies to explain how to tell which one is a metal, which one is a non-metal, to tell which group. I think I posted a question in our class. It's a table that has
yes,
different ionization energies, and you can use them to tell which group does an element belong to, and so on and so on. Okay,
yeah,
so you can, or you can go and try it. However, not now. So let's talk about the electron affinity. Now with electron affinity, this one is the opposite of ionization energy, whereby in ionization energy you lose electrons. Here in electron affinity, you gain the electrons. Not so?
mm,
So therefore, it is the enthalpy change, or if you want to be specific with the first electron affinity, you can say it is the energy released when an electron is gained by an isolated gaseous neutral atoms, okay, to form a negatively charged gaseous ion. And this is what we are talking about. You have here your gaseous ion, so your gaseous atom, okay, this is your gaseous atom, and the gaseous atom receives an electron to form what we call a negatively charged gaseous ion. So if this happens, then this is electron affinity. But for ionization energy, it's the reverse. You have your gaseous atom, this is ionization energy, okay, and the gaseous atom loses one electron to form a positively charged gaseous ion, okay, and this is the electron that it lost. Not so? So this one becomes ionization energy, whereas this one becomes electron affinity. So the electron affinity is the opposite of ionization energy. Who has joined? Who has joined? Nobody? So now, the enthalpy change, the energy that is released when an electron is gained by a gaseous atom to form a negatively charged gaseous ion, is the electron affinity. Okay? Now for the first electron affinity, the values are negative. But for the second, third, fourth, fifth, sixth, seventh, 20th, the values will be negative. Okay? Should I repeat? The first electron affinities are negative, even for the high electropositive elements. Okay? In other words, when an electron is added onto an atom, energy is going to be given out. And so the reaction becomes exothermic. And the higher the energy that is given out, the higher the electron affinity. So now, how can you explain that? How can you explain the negative values of the first electron affinity and the negative values of the preceding electron affinities? It's simple. A moment, guys, a moment. Ati? Hey, okweyo kuzahaliyo. Amin. Okay, it's okay, guys, I'm back. Somebody was just talking to me. So for the first electron affinities, the enthalpy change is negative. Energy is given out. And why is energy given out? It is simple. Now, when we were studying, we studied what we call Ionic Radius, and we say that the nucleus is positively charged. Not so. You have many positives. You have many positives within the nucleus, okay? And you have negatives. Okay, the negatives do surround the nucleus. You have the electrons. Now, as the electron is coming, okay, to join this atom, okay, the incoming electron is going to receive a high force of attraction from a positive nucleus. There is high attraction force of attraction for this incoming electron as it is going to join, okay, this atom. Now, when finally this electron successfully adds itself on the atom, okay, the electron has been successfully added on the atom. Still the atom, you have many positive ions, positive charges inside. The other force of attraction, okay, this force that was pulling this electron to be added itself on the atom is going to be lost, okay, and that is the energy that will be observed. So the higher the force of attraction, the higher the energy that is going to be lost, okay, and so the higher the exothermic. And so the higher the attraction, the ease at which the electron is going to be added into the atom. Okay? And so that one accounts for why the first electron affinity is negative. But the rest, the second, third, fourth, fifth, sixth, seventh, they are positive. Why are they positive? After adding this electron, okay, this electron that you've added, the incoming electrons, if you are going to add the second, maybe the incoming electron, maybe you are adding the third, the incoming electron, this second electron that is going to be added, is going to receive a high force of repulsion. It's going to be highly repelled by this electron that was added. Okay? Okay? It is going to be highly repelled by this electron from accessing the nucleus. So as a result, you need to apply some force to forcefully overcome this repulsive force that is being provided by this electron that has been added. Okay? And so that is the energy that you use to add this electron to the atom. So therefore, makes the second to be positive. Energy is absorbed in the reaction. And if you are to add the third, same. So the energy increases. Why? Because for the second, you are receiving repulsion from one electron. But now when you add this one also, now you receive repulsive force from two. So the energy increases. The third, same thing, energy increases. The fourth, same thing, energy increases. But for the first, that force of attraction from the positively charged nucleus, okay, is the one that is going to be given out, which makes the first electron affinity to be exothermic. If you have a question, drop it in the chat box. I'll be able to find it. So basically, that's what we are talking about. The second is accompanied by absorption of energy, i.e., it is endothermic. The incoming electron experiences greater repulsion from both the outermost electron and the negative ion. Remember, when you add the electron, the ion becomes highly negatively charged, and also the electron is also negatively charged. Okay? So to overcome that repulsive force, then you must apply some force. Additionally, when you add an electron, the ionic radius increases. Okay? And the effective nuclear attraction for the incoming electron decreases. So as a result, you will need to add in some force to forcefully add the electron onto the atom. And it's as simple as that. So they are not experimental, thus they are not accurate. And so as a result, we determine them from the Born-Haber cycle. Now we shall study this in thermochemistry. Okay? Where we conduct different reactions, and those reactions, they can be determined experimentally. And then from the Hess's law, okay. So we shall study this, okay, in thermochemistry. Now let's see variation down the group and variation across the period. But let me first check the chat box. You never know, somebody might have a question for me. Oh, it's Amon who joined. Yes, Amon, you're welcome. Good morning. Yeah, better late than never. Any question for me? So let's see how our electron affinity is going to vary across the period. And it is simple. If you understood that concept of atomic radius, also this one becomes easy. Okay? This one also becomes easy. If you understood the concept of ionization energy, then also this one becomes easy. Across the period, you know that atomic radius decreases. Now we have said that electron affinity, you are adding electrons onto the nuclear, onto the atom. And we have said that as the electron is being added, it receives some force of attraction from the nucleus. So if atomic radius decreases down the group, sorry, across the period, then you expect the force of attraction to increase. So now can you guess? Can you guess in your mind? You should be thinking about how the electron affinity is going to vary. Okay? Down the group and across the period. Which is basically just some simple science. Let's talk about the science. So across the period, electron affinity increases. And this should be the very first statement to write. This is the first statement you are supposed to write. If you have to first tell us how it is going to vary. Is it going to increase or it is going to decrease? That should be the first thing you tell us. And across the period, and this is across, the electron affinity increases. Why is it increasing? It's because the atomic radius is decreasing across the period, and so the effective nuclear attraction, the effective nuclear charge for that incoming electron increases, or the effective nuclear charge of the atom increases, which increases the nuclear attraction for that incoming electron. And I hope you know why the atomic radius is decreasing across the period. Okay? So now if you increase the nuclear attraction for the incoming electron, then when the electron is added onto the atom, then more energy is going to be evolved. And if more energy is evolved, then the electron affinity is going to increase. Okay? Across the period. Somebody is going to say, as you move across the period, which is okay. Do you stand up and walk? I don't know. However, that was a general trend. However, we do have abnormalities. Like I told you, that's how we describe this. You first give a general trend, okay? You first say generally, electron affinity increases across the period. And you give that general trend. You give a reason why it is increasing. Then after giving a general trend, then you give those abnormalities. So however, we have the abnormalities. The electron affinity of beryllium, magnesium, nitrogen, and phosphorus. They are less exothermic. Okay? They are low compared to other elements. Why? Because these ones, they have a stable electronic configurations. Let's talk about beryllium. Beryllium, isn't it 4? Isn't it atomic number 4? Which is 1s2. And then 2s2. Then magnesium, it is the outermost. Let's just focus on the outermost. This is going to be neon. Okay? Ne. and this is just 3s2. Okay, this is magnesium. With nitrogen, it is going to be 1s2. 1s2. Is this beryllium? What is the atomic number of beryllium? I think, yeah, it is 1s2. It is okay. Nitrogen is going to be 1s2, 2s2, and then, yes, and then 2p3. This is nitrogen. So my aim is on the outermost configuration. And then phosphorus, it is going to be neon, Ne, and then 2s2, and then, no, this is 3s2, and then 3p, 3p3. Now, from these configurations, for phosphorus, you are adding the electrons on the 3p orbital, which is half filled. You see? So, it's okay, guys. Somebody was talking to me. So we are adding electrons on the 3p orbital. Okay? We are adding electrons on the 3p orbital, which is half filled. So we say that the 3p orbital has 3 suborbitals. The p orbital has 3 suborbitals. So it is half filled. You have electron here, you have electron here, you also have electron here. So it is half filled, like how you see this. So now what does that mean, being half filled? It is thermodynamically stable. So adding the fourth electron, you'll be destabilizing, okay, this configuration, this atom. So it relatively offers less force of attraction, less attractive force. Okay? And so that's why the addition of that electron is going to be less exothermic. Even when you are adding on magnesium, you are adding on the 2s electron, and the 2s is full. It is fully filled, and a fully filled orbital is thermodynamically stable. And so it being stable, it relatively offers less force of attraction to the incoming electron, and so less energy is going to be evolved when the electron is added into the atom. Okay? Yeah, so basically that's how simple it is. However, down the group, the electron affinity decreases for all atoms. Why? Because the atomic radius is increasing down the group. And so the effective nuclear charge of these atoms is going to decrease. And if the effective nuclear charge decreases, then the nuclear attraction for the incoming electron decreases. And so if it decreases, then less energy is going to be given out when that electron is finally added onto the atom. Is that okay? Can I receive your questions? So from your question, okay? Yes, you are telling me that you are coming. It's kind of confusing. One there is attraction, less repulsion, less attraction. It is simple. With this electron affinity, okay? You have a gaseous atom, and the gaseous atom receives an electron to form a negatively charged gaseous ion. Now for this electron to be added onto this gaseous atom, okay, then this gaseous atom must offer some attraction for this incoming electron. Okay? For the first electron affinity, it offers some attraction for the incoming electron. And the higher the force of attraction, okay, then the higher the energy that is given out when that electron is finally added onto the atom. Now, if the force of attraction is high, that is for the cases of across the period, because across the period the atomic radius decreases, and so if the radius decreases, then atoms become small, and so the effective nuclear attraction for the incoming electron becomes high. So if the nuclear attraction for this incoming electron, this one, is high, then it means much energy is going to be given out when finally this electron is added onto the gaseous atom. And that's why the electron affinity is going to increase across the period. But however, in the case of down the group, where the atoms increase in size, the electron affinity decreases. Why? Because if they increase in size, then the effective nuclear charge for that atom decreases. And if the effective nuclear charge decreases, then the nuclear attraction for this incoming electron decreases. Okay? And so as a result, less energy is going to be given out when finally this atom is added onto the gaseous atom. Is that okay? Yes. I hope it's okay. Somebody is complaining about the effective nuclear charge. Now, the effective nuclear charge, it is that resultant force that occurs as a result of nuclear charge and screening effect. Like I told you when we were explaining atomic radius, I told you that the nucleus is positively charged. Okay? You have very many positives. And the number of positive charges within the nucleus of an atom is what we call the nuclear charge. Those are the number of positive atoms within the nucleus. And the number of negative charges, okay, the electrons that surround the nucleus, they bring about the shielding or screening effect. That since all these electrons are negatively charged, okay, the negatively charged electrons that are innermost, they shield, they screen, they repel these outermost electrons, okay, from being attracted to this nucleus. So that phenomenon is called the screening effect. So you have the nuclear charge, those are the positive charges, which attract these electrons, but you also have the screening effect, the shielding effect, the repelling of these innermost electrons to the outermost electrons from being attracted to the nucleus. Now, the two, the nuclear charge, the nuclear charge, and the screening effect, okay, they all occur within the same atom. But now, the resultant effect between the two, okay, maybe if nuclear charge is way higher than the screening effect, that is the resultant effect. Or if the screening effect is way above the nuclear charge, the screening effect outweighs the nuclear charge. Now that is the resultant effect. And the resultant effect is what we refer to as the effective nuclear charge. Okay, the effective nuclear charge. And if the nuclear charge is higher than the screening effect, then the effective nuclear charge increases. Alternatively, if the screening effect is higher than the nuclear charge, then the effective nuclear charge decreases. Okay? And if the effective nuclear charge decreases, then the nuclear attraction for the outermost, now depending on what you're explaining. But in this case, for electron affinity, the effective nuclear attraction for the incoming electron decreases if the effective nuclear charge decreases. And so if it decreases, then a little energy or less energy is going to be evolved when finally that electron is added onto the atom. But if the nuclear charge is high, then the effective nuclear charge is high, okay? And if the effective nuclear charge is high, then the nuclear attraction for the incoming electron becomes high. The incoming electron receives high attraction. And so if it is high, then what happens to the energy that is given out? When this electron finally adds onto the atom, much energy is going to be given out. So basically that is the concept. Is it okay now? Edwin?
Very okay.
Oh, very okay. That's very good. That's very good. So I hope you can explain variation of electron affinity across the period and variation of electron affinity down the group. And there is work in our classroom. Please endeavor to go and do it. So let's talk about electronegativity. And this one is just simple. Electronegativity. Electronegativity. Let me illustrate it as this. Assuming you are at school and it's break time, and you with your birthday, you all contribute 500 each, and you buy zombies of 10,000 of 1k, and they add you one nyongeza. Now you and your birthday, it is assumed that each one of you is going to eat 3. You eat 3, your birthday eats 3, because each one of you contributed 500. But it's not actually the case. One of you might be having a high affinity for the zombies. Maybe you have a high affinity for you, as your friend eats 1. By the time your friend finishes 1, for you finished 3. So in the end, instead of assuming that each one of you is going to eat 3, you find that one is going to eat 5 and the one eats just 1. Or one is going to eat 4 and another one eats 2. Okay? And the zombies will be unequally shared. Is that okay? So bring that analogy here with electronegativity. You have your 2 atoms, and the 2 atoms are covalently bonded together. And from a covalent bond, it means that sorry, since these atoms are covalently bonded together, it means that this atom A contributed 1 electron and this atom B also contributed 1 electron to this covalent bond. And so as a result, you have a covalent bond, like 500 each. Now, as if that is not enough, these atoms, they have different sizes and so different affinities for these electrons, for the bonding electrons. So because one atom is greedy for the electrons, eh, it is greedy, it has too much greed for the electrons. Maybe atom B has too much greed for the electrons than atom A. The atom B will attract these bonding electrons, okay, within this covalent bond more towards itself. And so as a result, we shall form atom A. Yes, the bond will remain there, but since the atom is has withdrawn the bonding electrons, it will assume a negative charge, but it is partial. Okay? It is partially negatively charged. And since this one has given up on the electrons, it will assume a positive charge, but also the positive charge is partial. It is not full. Okay? So if I bring this back to you and your friend, this is your friend who has eaten 4 zumbis, and this is you who has eaten just 2. Now therefore from this, how can you define electronegativity? You want to define it? Edwin?
Is a tendency where an electron attracts bonding, it attracts the bonding electrons towards itself.
Okay. He's saying that it's a tendency where an element tends to attract the bonding electrons towards to itself. Okay, that's good. Did you copy it somewhere or you got it from your neurons, from your mind, from your brain?
You are
Okay,
the one who told me that one is attracting all the electrons itself.
I'm the one who has told you that, eh? Okay, that's good. That is good. So, one is going to attract. Actually, what you have just defined is the true definition of electronegativity. And you can check on this. It is the tendency, okay, of an element to attract the bonding electrons. What are the bonding electrons? The electrons within this covalent bond. They are the bonding electrons. If you just say electrons without this word, I will cross you. Because we have different types of electrons. We have bonding electrons, we have lone pair of electrons, and yeah. So if you just say bonding electrons, I'll say which electrons. So if you just say electrons, I'll say which electrons. So here you attract the bonding electrons towards itself in a covalent bond. And it is as simple as that. And I've already illustrated that. You have atom A and B, and the two atoms are covalently bonded together. Okay? The two atoms are covalently bonded together. One is going to be more grid. And now more grid, in this case, is more electronegative. So one atom is going to be more electronegative than the other. So the more electronegative atom attracts the bonding electron towards the other, and the less electronegative atom loses the bonding electrons. Okay? Yes. And you need to know the factors which affect the electronegativity, and the factors include the atomic radius, screening effect, and nuclear charge. Actually, if you are to observe all these ones, they do affect the atomic radius, the size of the atom, and since they affect the size of the atom, then they will also contribute to the electronegativity. And let's see how. Before the variations, if nuclear charge increases, then the attraction of the bonding electron increases. If screening effect increases, then these bonding electrons, they will be poorly attracted. And if the atomic radius increases, then the size, okay? So you cannot compare these two atoms. One atom has a smaller size, another one has a large size. One is that one, and another one is that one. And these two atoms are covalently bonded together. So you have the center here and the center here. So this, if you have the two electrons within this covalent bond, to which atom will the electrons be more attracted to? Obviously the smaller atom. Okay? So it is this one that will be more electronegative, and this one will be less electronegative. And so this one will try to attract the bonding electrons more to itself. Is that okay? Yes. So let's see how electronegativity varies across the period. Obviously it increases. Why? Because the atomic radius is decreasing. Let's do the rubbing. So variation across the period. So electronegativity increases across the period. Why? Because atoms are becoming smaller and the effective nuclear charge is increasing. Therefore, the bonding electrons, they will be strongly attracted to the nucleus. But whereas down the group, sorry for that, down the group, the sizes of these atoms or the size of these atoms is increasing. Okay? And if the size increases, then what does that imply? It implies that such a big atom, if it bonds with another atom, this one, the nucleus will be far away from the bonding electrons within here. So these bonding electrons will be poorly attracted to the nucleus, hence decreasing the electronegativity. And this concept is so good as far as organic chemistry is concerned. And it will be frequent. It will be frequent. And we shall talk about it as many times as we can. Is that okay? Any question for me? Okay, so let's talk about electropositivity now. Now, I can say this one is more opposite of electronegativity. Whereas electronegativity is the attraction of the bonding electrons, okay, in a covalent bond, this one is the ease to lose the electrons to form positively charged ions. Okay? The ease, how easily can you lose the electrons? Okay? To form positively charged ions. And here that's where your metals come in. The sodium, the potassium, the calcium, the magnesium, those ones. They can easily lose their electrons. Okay? In the outermost shell. And if you easily lose the electrons, then the higher the ease of losing electrons, the higher the electropositivity. So that's why you expect electropositivity to decrease across the period. Okay? And electronegativity increase across the period. For example, the sodium ions in group 1 and the chloride ions in group 7, which one easily loses the electrons? It is sodium ion. So the sodium is highly electropositive. And which one easily gains? It's the chloride. And so the chloride becomes highly electronegative. So if you can understand that basic, then you'll be good to go. So property of metallic elements, because they have few electrons in the outermost shell, and so they can easily lose their electrons. Hence, low ionization energy. Down the group, of course, you expect electropositivity to increase, because down the group, you're going to increase the atomic radius, okay? And if you increase the sizes, then the force of attraction for the outermost electron decreases. The nuclear attraction for the outermost electron decreases. And so if the nuclear attraction decreases, then you easily lose that electron. However, for across the period, so the most reactive metals are found at the bottom, okay? That's why lithium in group 1 reacts slowly with cold water due to low electropositivity. But potassium, sodium, they even react with formation of a flame. They form a flame as they are reacting. Why? Because they are highly electropositive, so they can highly react. But for across the period, before the charge density, for across the period, then the electropositivity decreases. Why? Because the atomic radius decreases. So the effective nuclear attraction for the outermost electron increases. So it becomes hard to lose that electron. And so the decrease in electropositivity. Is electropositivity okay? Is it okay?
It's okay.
Okay, that's very good. That's brilliant. So let's talk about the charge density, and then we call it a day. And the charge density, this one is the ratio of charge of an element to the to the ionic radius. Ratio of charge of an element to the ionic radius. So in other words, it is charge, okay? Charge to the ionic radius. So if you understand that, then you'll be good to go. So it is the ratio of charge of a given ion to its radius. And what does that mean? It is this guy who first studied the charge density called fusion. Okay? And he told us that polarization. Now, polarization means the distortion of the ionic cloud on a given atom or element by another element. Like how we did. If you have chloride and if you have carbon and the carbon is bonded to oxygen, this oxygen is highly electronegative than the carbon. Okay? So anyway, this is something different. This is electronegativity. Let's say you have aluminium, okay? And the aluminium is bonded to chlorine. Okay? So now because the aluminium has a high polarization power, and we are going to see what polarization power is, it is going to distort the electron cloud. Okay? on the chlorine, okay, by putting the bonding electrons between the aluminium chloride bond. So this bond, instead of being purely ionic, it will be totally distorted from being ionic, and the bond turns into a covalent bond. Okay? More of a covalent bond. And we are going to explain different things when we reach there, so have no worries. So the polarization of any element, it will always depend on, number one, the charge density. And aluminium has a very high charge density, because see, it forms these ions, aluminium 3 ions. So it has a charge of +2. But the ionic radius, remember, across the period, the atomic radius decreases. So sodium, okay, has relatively higher size, followed by magnesium, higher size also, followed by aluminium. So aluminium, as if that's not enough, you even lose the 2 electrons. Okay? So as a result, the ionic radius of this aluminium is going to be very small. Okay? Very small. And remember, it has a high charge. Okay? The charge is so high. +2. Sorry, +3. So when you get the ratio, okay, the ratio of charge to ionic radius, that ratio is going to be so high. Okay? And it is that ratio which we term the polarization power. Okay? The polarization of a metal atom or metal ion. And the higher the polarization power, then the higher the distortion. For example, if you have reacted the aluminium with a chloride atom, this one will have a high polarization power, and this one will have a high polarizability. So this one will highly be polarized. And if you polarize this aluminium chloride bond, it will totally change the physical and the chemical properties of such a compound. For example, the aluminium chloride, it is AlCl, AlCl3. This one is assumed to be an ionic compound. But do you know that it has more of covalent, it is more of a covalent compound? It can dissolve in organic solvents. Why? Because the bond, the aluminium chloride bond, has been distorted, and it is more of a covalent bond now. And so it will easily dissolve in organic solvent. Is that okay? Yes, Edwin? Yeah, we can use this example. You can check on this. You can check on this. For example, you are given the melting point. Let me change. Let me get some. So you have the melting point of chlorides, and you have sodium chloride, magnesium chloride, and aluminium chloride. You can check on their melting point. So since they are believed to be ionic compounds, they are assumed to have high melting points. Okay? And you check on this sodium chloride. Yes, it is high, 801. Magnesium chloride, it is also kinda high, but it is decreasing. How can you explain this decrease? But aluminium chloride now, for it, if it is heated, it sublimes. That means it has very low melting point. It doesn't even pass through the liquid phase. It just sublimes from solid and then to gaseous phase. So how can you explain this decrease? Yet according to the factors which affect an ionic bond, the factors which affect the melting point, these ones being ionic compounds, they are assumed to have high melting points. and even the factors which affect the strength of an ionic bond depends on the number of electrons that are contributed formation of that bond. And this one uses 3, this one uses 2, but this one uses 1. However, this one is more stable, requires relatively high energy than this. So it is disobeying the laws of ionic compounds. So which explanation can you give? It still goes back to charge density and polarization. Okay? In that polarization, in that in this, the aluminium having a high polarization power, how do you know? It has a very high charge of +2, but it has a small, okay, ionic radius. Ionic radius. Why? Because atomic radius or ionic radius decreases across the period. So this one is smaller than this and than this. So having a high charge with a small ionic radius, but with sodium has less charge, just +1, with a high ionic radius. So it means that the aluminium has a high polarizing power that polarizes the aluminium chloride bond. And if you polarize the bond, then it ceases from being ionic, okay, to becoming now more of a covalent bond. And so when you increase the covalent character, then you reduce the strength of an ionic bond. And remember, covalent compounds, they have low melting points and boiling points. And so this one, the aluminium chloride of ours, is going to have a low melting point. Is that okay? Any question for me? Let's try to make it clear. So the concept of polarization is still hard. Like I told you, polarization means distortion, ability to attract. For example, let's talk about how aluminium chloride is formed. Aluminium having an atomic number of 13. It has, okay, its electron configuration is going to be Ne, okay, then 3s, 3s2, and then 3p1. So from this electron configuration, aluminium is going to lose these 3 electrons to form aluminium 3 ions. Okay? So it has a high charge. Okay? And having a high charge, its ionic radius is very small compared to these other members. But it has the highest charge of all the 3 members. So therefore, if you take a ratio of charge, okay, let me write charge, or if you take a ratio of charge to ionic radius, okay, the ratio is going to be big, okay, than these other elements. So what does that mean? It has a high polarizing power. It highly polarizes, okay? It has a high polarizing power. In that, when aluminium therefore forms an ionic bond with another non-metal such as chlorine, having a high polarizing power, it will greatly distort the electrons on this chloride. Remember, ionic bonds are formed by you the metal, you lose the electrons, and then the electrons are received by a non-metal to form a negatively charged ion. And so for you, when you lose, you form a positively charged ion. So this chlorine, after it has received the electrons, then they will attract each other. This one being positively charged and this one being negatively charged, they will attract each other. And so in the process of attracting, since this one is very small, okay, I can illustrate it as this. it is very small, and the chlorine being large in size. If the two are bonded together, okay, this is small, whereas this one is large. These electrons, these outermost electrons, they will be close to the nucleus of this aluminium than how they are close to this nucleus. So as a result, they will be strongly attracted to this nucleus of aluminium, okay, than how they are attracted to the nucleus of chlorine. And so that attraction by a metal atom, so the metal ion, okay, to these electrons is what we call the polarization. So this ionic bond is going to be highly polarized. And so when you polarize an ionic bond, it changes from being an ionic bond from purely ionic to more of a covalent bond. And remember, covalent bonds are weak, and covalent compounds, they boil at very low temperature. Okay? And so from that, what does that mean? It means that the aluminium chloride is going to boil at very low temperatures compared to these two, magnesium chloride and sodium chloride. But even across this, there is a decrease in melting point. This is melting, not boiling. There is a decrease in melting point. Why decrease? Because the magnesium has relatively high polarizing power than the sodium ion. So this bond, the magnesium chloride bond, it will be kinder polarized than in sodium. Now in sodium, for it one, it will be purely ionic. Okay? Yes. I hope it is now okay. Yes. I hope it is now okay. That's good.